Assalamu alaikum. Welcome to lecture 23 of natural language processing. So I hope all of you are doing well and keeping yourself protected. So today we will continue with our discussion on recurrent neural networks. We had already studied the standard unidirectional recurrent neural networks, and we discussed the basic equations governing such a neural network. So today we will discuss some, you can say, extensions or variations to the recurrent neural network that were designed to handle some of the issues that were seen in the standard recurrent neural network. So we will talk about the gated recurrent unit, GRU, and LSTM, which is a long short-term memory network. After this, we will also discuss some, you can say, general considerations while designing neural networks and deep neural networks, where we'll talk about things like overfitting and the vanishing gradient problem and the exploding gradient problem, and things like dropout and batch normalization and so on. So that is basically the agenda for today. In the next lecture, we will talk about the transformer. So that is the idea for today as well as for the next lecture. So are there any questions before I get started? So we had discussed the standard recurrent neural networks, and I will write the recurrence equation again for starters. So the main recurrence equation in the recurrent neural network is like this. We have a output A at time t. So this is given by some function, usually a tangent hyperbolic function. You have a weight parametric matrix AX. This is a matrix, of course. This multiplies with the vector X at time t, input vector at time t. And then you have another weight matrix AA, which multiplies with the output at the previous time interval A t minus 1 plus B A. So this is the standard recurrence equation for the recurrent layer or the hidden layer of a neural network. As you can see, information from previous time steps is carried through the vector A t minus 1, which is the output of the hidden layer at the previous time step. And that, of course, would capture information from t minus 2, and that would, of course, capture information t minus 3, and so on. So theoretically, in this way, you can bring information from very far behind in the time series, in the sequence. And as such, theoretically, a standard recurrent neural network can capture a lot of memory from the start of the sequence. But in practice, of course, there are some issues which we will address through the two models that we are going to discuss today. But before that, let me rewrite this recurrence equation in a simplified format. And this is also used in the slides, in the videos that I shared with you. So we will write this as AT, the function G, W, A, X, A plus B, A. So what is happening here is that we have combined the parameter WAX and WAA into one parameter matrix WA. And we have combined the two vectors A from the previous time step, AT minus 1, and X from the current time step into one single vector XA, sorry. Okay, so So this kind of simplifies the notation somewhat, although it will give you the same result. So if we say, for example, WAX, so AX basically is a matrix, parametric matrix of size, let's say 100 by 300. This is just an example. So meaning that input X is of size 300 and hidden layer, recurrent layer is size A, is 100. Then of course WAA would be 100 by 100. So if we combine both of these matrices into one matrix, WA, the new matrix would be of size. So our vector A is of size 100, right? So our first matrix WA would then be 100 by 400. So now the WAA matrix is kind of concatenated to the right of the WAX matrix. Okay, WAA matrix was 100 by 100. We have concatenated it to the right of WAX matrix. As such, WAX matrix has increased in size to 400. Okay? And similarly, our XA would then be of size 400. So this is basically, of course, 300 of vector X plus 100 after that of vector A of the previous time step. So in this way, you carry only one parameter matrix, which is WA, and one bias vector, which is BA. So this is just a notational simplification. There is no change in the computation as such. Of course, if you follow this notation, then of course YT can also be written as WY and basically we have A, so we'll write an Y there as well, just to make sure the notation to be consistent, plus BY. Okay. Of course, this A is at the same time step T. Okay. So these are the standard equations for a standard recurrent neural network. So any questions here so far before I start into the next model? Okay, so we mentioned last time that one of the issues with this standard recurrent neural network is, of course, theoretically, you can retain information from the start of the sequence to later part of the sequence, but that information would be diluted over time, over sequence, because a lot of information would come in between it. So I gave the example of a sentence like the flights that were scheduled to depart to, for example, Dubai, Lahore, Karachi, etc. were cancelled. Okay? So this is a long sequence of words. And this is, of course, an example, and there could be many other such examples. So this verb here, were, is in the plural sense or tense. And this is in the plural tense because we talked about flights in the plural here. If flights was flight, then that verb would have been was, singular. So Of course, when you're feeding this to a recurrent neural network, you would need to retain this information that flights was plural when you reach that stage of deciding what word should come at the position were. So if you use a standard recurrent neural network, that information might be lost because of the various numerous intermediate words that come before, between flights and were. So to handle this issue, and of course, there's an issue of vanishing gradient as well. I mentioned this last time, but it's less important. It is important, but less important in the context of a simple standard recurrent neural network. So we'll talk about vanishing gradient again later today, but this is one of the main issues. So to address this, people have proposed modifications to the standard recurrent neural network, and we'll talk about two modifications. One is called the unit or GRU. So GRU actually was proposed later on. I think it was, I don't know the exact date, but I think around 2007. It's slightly simpler. And the other model was the long, short term LSTM. And this was proposed before 1997, when even neural networks weren't that popular. But it was kind of seminal paper then. This model is a bit more general, more flexible. So instead of following the historical perspective, we'll discuss first the simpler model, GRU, and then discuss the more flexible or general model, LSTM. So these models use the idea of a memory cell. Or you can say cell is similar to like a unit or a neuron. So these terms are used interchangeably. So of course, in a GRU, the hidden layer is now consisting of GRUs, gated recurrent unit. In the standard RNN, they're composed of the standard recurrent unit. Okay? So the main difference is, of course, the unit is different. In the RNN, you have the standard unit. In the GRU, you have the GRU. In the LSTM, we have the LSTM unit. Okay? And within this unit, there is a notion of memory. Okay? So remember, the layer is a vector. Just like we gave A as the output of the vector, we wrote A because as a singular without bolding, but in general, this is a vector. It could be 100 units. Okay? So similarly, you have a memory cell, C, corresponding to that layer, which we call C. Okay? So this is the, okay? So this memory cell vector is then controlled through gates. So information in this cell is controlled through gates. Gates, of course, you understand it from a purely physical concept as a device that protects information from going from inside and outside. So you can think of this in the same way. So there's a function, you can say, that decides what to put inside the cell and what not to put inside the cell. It's like a gate, physical gate. So now, again, as for RNN, as I said before, understanding these models is much easier using equations. So we'll be using equations again, rather than trying to draw complex figures. So and we will be using notation that are kind of consistent with GRU and LSTM. So that there's less confusion. So in general, AT is set equal to CT in GRU. We are talking about a GRU right now. Okay? ठीक है. So, and then at each time step, we generate a candidate information that we would like to update, or that would be potentially used to update the memory cell. So that candidate we say C prime. Okay? And this is the same equation as before for the standard recurrent neural network. CT W A X A plus BA. Okay? So of course CT पे हमने so XA का मतलब क्या है, इसमें XT है और AT minus 1 है प्रीवियस आइट्रेशन A की वेक्टर में. ठीक है. But we don't right away change our memory cell information, but we put it into a candidate C. ठीक है. C prime. Of course, given के जो हमने previous notation use की थी, इसको हम यूं भी लिख सकते हैं, C कर देते हैं. ठीक है, यूं भी कर सकते हैं if you want to. But of course, if you can understand the previous equation, that is fine as well. Okay. Okay. So now this is a candidate. Now this candidate, from this candidate, will decide the output for this time step. So the output C T is then decided using gates. Okay, so was there some question? Okay. So can all of you hear me?
Yes, sir.
All right. So let me then continue. So the output now would then be based on gating of this candidate as well as the information from the previous time step. So what is that? Let me write it first and then I'll explain it to you. So we have a vector gamma. I just use G, not use gamma, GU, which we call the update gate. So this update gate would multiply with the candidate that we have generated at this time step plus 1 minus the update gate into the value of the memory cell or the output at the previous time step. Okay. So this is actually the main equation of the gated recurrent unit. Okay. So we had each time step we have generated a candidate just like in standard recurrent neural network, but we do not right away call that as the output. We gate it, we pass it through some filter. And the output is decided by a gate applied to the candidate that you generated plus 1 minus the gate applied to the previous value. So this GU, as I said, is a vector, of course, vector of length equal to, of course, of A and C. Okay? So this is equal to the size of the recurrent layer, the size of the GRU layer. And it has values, all its values are within 0 and 1. Okay? Within the interval 0 and 1. And I'll mention shortly how we get that 0 and 1. But let's say, and most of the time the value would be either closer to 0 or closer to 1. So let's say at any given point in time, the equation that I wrote above there, so let's say this value was 1 at a particular point in time. So it means that we will take this candidate that was generated at this time step, and 1 minus GU would be then be 0, and we will discard the information from the previous time step that was in the memory cell and put this new value in the memory cell. So that is one way of doing it. In other words, you say you don't have any memory. Previous से जो भी information आ रही है आप discard करते जाएं and retain only the current information. ठीक है? On the flip side, let's say GU आपके पास 0 आ रहा है, so then the first term would be cancelled out, meaning that जो current input से आपके पास जो output आई है C prime, that would be zeroed, और जो पीछे memory में information आपने store की हुई है वो completely pass on होगी. And let's say if you do this for multiple times, then that information will be passed on and on and on. ठीक है? I mean, of course, this is again for explanation purposes. Let's say जो flights का जो था, यहाँ हमने जब हमने ये word पढ़ा, when we looked at this word, then let's say we had set GU to 0. Then whatever we had after this, it was all 0. इसका मतलब है कि when we came to were, it was still 0. It means that flight की information completely pass on होगी है to were, और बीच में जितने भी words थे उसकी information हमने नहीं include की. ठीक है? So now we have complete memory of flights from way back when we even reached a were. And of course, this happened when GU remained 0 after flights until were. Okay? And of course, if you put GU as 1, then you discard the previous memory. But as I said before, this GU is a range between 0 and 1. And this range is decided by another adaptable, learnable function, which is usually a sigmoid of course, another parameter, W, ये था update gate था, U into X U plus BU. Again, the same notation that we have been using before. XU में क्या है? Current time step पे T है, और previous time step में जो A output था, AT minus 1. So that is used to decide this vector. This GU, as I said, is also a vector. And this function sigmoid is applied element-wise, meaning that each value in the cell would be between 0 and 1. जैसे आप apply करते हैं for binary classification. So in other words, हर एक cell की value can be controlled through this adaptable model by a value from 0 to 1. And as I said, since this is sigmoid, sigmoid में ज़्यादातर value ज़्यादातर 0 की तरफ जाती है या 1 की तरफ. Of course, बीच में थोड़ा सा portion होता है, उसमें between 0 and 1 भी हो सकती है. So using this adaptable and learnable function, you can control the gate for each output of the hidden layer. ठीक है? So coming back to our original function, so this was our main recurrence equation. Now GU is also learned adaptively C prime, of course, is also learned adaptively and is the candidate value for the current time step. And then, of course, CT minus 1 is the memory at the previous time step. And the gate then controls each of those values of the vector C prime and C to decide what to pass on to the current time period. Okay? And then, of course, as I said before, the actual output of the GRU is equal to CT. LSTM में ये भी डिफरेंट होता है, बट GRU हम पहले डिस्कस कर रहे हैं. तो GRU में जो मेमोरी सेल की इंफॉर्मेशन at any given point in time is the actual output for the next, and then that is basically used in the next time step. So this essentially is the gated recurrent unit. And as you can see, we are using a functional gate, functional form, a mathematical gate, you can say, to control each output of the hidden layer to decide whether we like to keep the current information or to discard the current information or retain the previous information or discard the previous information. And you can do this iteratively to keep theoretically again information from very far behind. Exactly. And the most important thing is all adaptable. Remember, GU is also learned by a function f, which has parameters. So these are parameters. Okay. So WU would of course be 100 by 100. Let's say if your recurrent layer is 100, and let's say it will be 100 by 200 if उसके ऊपर previous iteration का भी आ रहा होगा. Because remember our notation that we mentioned कि हमने दोनों W में WA so क्या था ये WU AU जो है उसमें हमने दोनों previous A भी डाला हुआ इसके अंदर X के अंदर. ठीक है. So it's a simplified notation. In some other models, slide further एक और गेट भी कई दफा यूज करते हैं. And that is applied different places. एक place तो होता है they put it here. We have another gate which we call the relevance gate. And the whole information within the parenthesis is multiplied with the relevance gate. And this gate also is of the same size and is computed in a similar way. But this now controls के जो current information memory cell है वो कितनी relevant है. उसके ऊपर पूरा एक और filter या gate लगा दिया. So sometimes this gate is also added in a standard GRU model. By the way, ये GR जो है ना sometimes इधर डाला जाता है, sometimes ये C को modify करने के लिए डालते हैं. एक सेकेंड, इधर आएगा. ठीक है. So of course I have written this in both ways. एक ही जगह होगा, either at the end that is more common or right at the front of C. उसको change कर रहा है. ठीक है. C prime. But since all of these are adaptable, the idea would be that you would be able to learn this from data. हमने खुद ही कुछ नहीं पैरामीटर सेट करना. We are not worrying about how to set these parameters. Those parameters are learned through data using the simple BP algorithm, of course, with slight modifications to cater for all of these other parameters. So any questions? So now let's move on to LSTM. LSTM, as I mentioned, was actually proposed earlier on, but at that time, recurrent networks as well as deep neural networks weren't that popular. And this model was actually more general than GRU. Later on, people proposed the GRU, which is slightly simpler than LSTM. So, but let's look at the LSTM, very similar idea using gates, but now you have more gates. And as such, you have greater control or flexibility over how you pass information from previous time steps to newer time steps. So the main equation, let me write C prime, sorry. C prime is of course computed the same way. Sorry. Is the tangent hyperbolic most likely W, C, X, C plus BC. Okay? So this is a candidate at a particular time step. Of course, XC जो है, it includes XT and previous time step का जो A है, output is always A, AT minus 1. Now how do we decide the actual CT? Now the gating is somewhat different. Now we have two gates. We have G update with the candidate that is generated at this time step, plus we now have a separate gate, which we call the forget gate, for the output or the memory cell value at the previous time step, T minus 1. So this is the memory cell value at the previous time step. Okay. So now instead of previously GF was 1 minus GU. So kind of complementary tha pehle. But now you have a separate, you can say, gate for the information that you want to pass from the previous time step. So that is controlled independently as compared to the update gate. And of course, these gates are computed in the same way. So that is one difference. The second difference is the output A, T, before was actually equal to CT, right? GRU में ये same था. But now we have another gate here, which we call the output gate. So this output gate, by the way, is a vector, and this vector multiplies element-wise with this C. So multiplication is also element-wise. It's not a vector multiplication. पहला element of C से multiply होगा, दूसरा element दूसरे से multiply होगा, and so on. So kind of आप कह लें कि weighing कर रहे हैं हम हर एक element. And of course, all of these G's are computed in the same way. For example, G naught is sigmoid. यहाँ sigmoid ही होगा हमेशा, because we want the value to be between 0 and 1. And we'll use the same notation, G0, X0 plus B0. B0. B, yeah. O, output. तो इसी तरह R के लिए भी होगा, इसी तरह F के लिए भी होगा. So if you talk about GF, F, so this is again sigmoid, W, F, X, F plus B, F. Okay. And GU, of course, is the same as before. So now we have 3 gates, and each of those gates have learnable parameters. All of these parameters are learned through from data using more or less the same procedure of backpropagation. Of course, procedure is exactly the same. Simply कि आप ज़्यादा आपके पास बीच में terms आ गई हैं, थोड़ी सी mathematical manipulation थोड़ी सी आप ज़्यादा कर रहे होंगे. So that is essentially what a GRU and LSTM is. And of course, previously we had looked at the RNN as well. And of course, output remains the same. Output YT, if you're getting the output at each time step, is some other function of W, Y, of A. A is the output, right? Y, again, using the same notation. Of course, this sometimes can be confusing. B, Y. Okay. So if you're using this for, let's say, POS tagging, you will get an output at each time step, which would decide the label, which is POS for each word that you have seen at that particular time step. And we have already discussed this before. If you want to do sentiment classification, you can only compute Y at the end of the complete sentence or at the end of the complete document. Intermediate Ys are not computed. So any questions here? Okay, now let's talk about some, you can say, other variations. So far we have talked about unidirectional recurrent networks, including GRU and LSTM. So we had talked about unidirectional RNN, meaning that you are processing information from left to right. But in many applications, it is often helpful to have information after the current time step. So you can have various examples. Even in POS tagging also, you might want to know what is the next word to better decide what is the proper tag for the current word. Other examples could be, for example, let's say, again, this example is used in the videos. Teddy was the president of USA. So Teddy here is not talking about any word. This is a proper noun, and it's actually a president's, you can say, nickname or also colloquial name. So if you're using name identity recognition, this should be recognized as a name of a person, not as, let's say, a small beer, for example. But to know that this is a name of a person, you need to know information that is coming after this particular point in time. Okay? So in many applications, actually, I would say in most applications for NLP, we would like to have information from the later time as well, including language modeling. Of course, there are some applications in which you cannot have information from a particular time period. For example, if you're doing speech recognition, real-time speech recognition. So obviously, आपके पास information at a particular time period, उसके पीछे वाली information होगी, आगे वाली information तो नहीं होगी. But if you have written text, saved text, and you can have information from following words, then you should use it, and in most applications, it will improve your performance. Okay? But as I said, if you're doing real-time speech recognition or text transcription or something like that, obviously you will not know what is going to happen afterwards. You will only have information that has passed. So uske liye standard recurrent unidirectional neural network will be fine. So how does a bidirectional neural network works? RNN. When I say RNN now, you can think of it as either GRU or LSTM also, because the layer that we are talking about, recurrent layer, could be standard RNN, it could be GRU, it could be LSTM. Okay? So bidirectional RNN uses two, you can say RNN layers side by side, or you can say in parallel, not stacked one after the, not one after the, but side by side. So मतलब यूं करके है. तो input is processed, one process information from left to right, the other process from right to left. And the output of both networks is then concatenated, or of course, there are other options also, at each time step. So let's say if I give an example, I live in Lahore, okay? So I'll call the left to right RNN R1, left to right. So this will process I, then it will process live, then it will press in, and then it will process Lahore. R2, which is right to left, will process Lahore, in, live, and I. Okay. So both of them will process, and they can do it in parallel. Serial नहीं है ये. मतलब of course R1 will process one by one. At the same time, R2 is also processing one by one. Okay. But now what happens? Each of those would output A. Let's say एक वाला A1 है at any time t, दूसरे का A2 है at any point t. So the final output of the network is then actually the concatenation at each time step of both networks' output at that particular time step. So the final output AT is basically, of course, there are many options: concatenation, spelling is right, of A1 T and A2 T. Okay? And now your final output would then proceed on this vector A, not A1 and A2. Okay? Of course, let's say आप process कर रहे हैं, आपने live process करना है, ठीक है? So live process करना है तो फिर आपने A1 का 2 लेना है, ठीक है? और A जो था 2 का, if you are counting from backwards, Lahore would be 1, in would be 2, and live would be 3. So these would be concatenated. Because हर एक word के ऊपर concatenate करना है, not arbitrary other words. Of course, you can do the sequence ordering in the same way to avoid confusion. तो राइट की ऑर्डरिंग 4 से शुरू होगी, 3 पे आएगी, 2 पे आ जाएगी. जब दोनों 2 पे होंगे, then you concatenate. ठीक है? So now the output A at 2 would have information of I as well as information from the right hand side, live, Lahore, and in. And then you can make the output based on that. So is this clear? So this is called bidirectional RNN, by RNN भी कहते हैं, and of course accordingly bidirectional GRU, bidirectional LSTM. Okay. Okay, moving on, we also can have multiple recurrent layers, or in other words, you can have deep networks. So far we have talked about only one one hidden layer, which was of course some RNN. So you can also have multiple RNNs, one after the other. So those are called then stacked RNNs. So for example, the first RNN may have output of 100, the second may have output of, let's say, 50, and maybe might have another, let's say, output of 25. And then maybe after that, you might have a feed-forward network also. Feed-forward network में पहले हमने जो अभी discuss किया, we only added one layer. So that could also be multiple feed-forward layers. Let's say 25 का एक feed-forward layer है. So this is, let's say, feed-forward. फिर उसको आपने 12 पे कर दिया feed-forward को. This is very small network. I'm just giving you an example. And then you have the final output. Okay. So you can have deep networks in this way as well. You can combine multiple recurrent units, one after the other, in which case we call them stacked, which means that if you talk about the first recurrent layer, recurrent network, अब इसको भी मैं A1 कह रहा हूँ. So A1, let's say 2 का जो output था, this would now feed into the input of the second recurrent network. Of course, it will be fed back into the first network also. Recurrence पहले पे भी चल रही है, but ये आगे भी जा रहा है to the second network. And then it continues in that fashion. So what I'm saying is कि let's say ये आपके पास पहला recurrent layer है, so दूसरा उसके बाद दूसरा है, फिर तीसरा है, and so on. So आपके पास इधर की जो output आगे जा रही है. Of course, हर एक layer की अपनी एक recurrence भी है, वो चलती रहेगी. ठीक है? But एक output आगे भी जा रही है, वही output आगे भी जाएगी to the next layer. And similarly, जो मैंने पहले बात बताई थी, bidirectional means that there are two recurrent networks. ठीक है, अब इन दोनों की जो output है, these are then concatenated to one A. And that of course concatenation is done at each word. ठीक है, so when the left to right model has reached that particular word and the right to left model has reached that particular word, फिर दोनों का output concatenate होगा. ठीक है. And then of course, as I said before, you can have multiple feed forward layer. Let's say ये recurrent layer है, so this is, let's say, recurrent, but आगे let's say आपके पास कई feed forward layers आ रही हैं. All of these are feed forward. Feed forward are fully connected, and then you have the output. Okay. So this is also possible. Okay. Okay. So that was about deep networks as well as bidirectional. Now let me talk about some general, you can say, issues and you can say considerations in neural networks or deep neural networks, including recurrent networks. So there are a number of things, and of course we won't be going into detail here. Of course, detail में कुछ math भी कई दफा आ जाएगी. But you need to know these issues, especially if you want to run some neural networks in practice. So first of all, let's talk about the vanishing gradient problem. We have already talked about this before. So the vanishing gradient problem stems from the issue of gradients becoming zero. So when the gradient becomes zero or very small, what happens? Updates do not occur. Remember, update में क्या होता है? W is equal to W old plus eta or minus eta into gradient. So if the gradient becomes zero, of course, there's not going to be any update. Your network is going to become static. It's not going to learn anything. When we talk about there's no update, no adaptation, we mean that there is no learning. And why does this gradient become zero? Because we are using mostly the sigmoid, for example, the tangent hyperbolic or the sigmoid function. And these are S functions, which are mostly close to 1 at high values and close to 0 at low values, and only a small region in between have a value or have values between 0 and 1. Okay? And when you talk about a deep network, our loss would typically occur or would be measured at the last layer, at the output layer. So from the output layer, and loss, of course, is what any difference, quantification of the difference between the true output and the output of the network. And that, of course, is the basis for our adaptation or learning. So that occurs at the last layer. So that has to be now propagated backwards to update all the layers, all the parameters till the start of the network. What typically happens is usually the change is higher because of gradient being not 0 or 1 at the end. But as you move back in the deep network, the change or the gradient becomes close to 0 or 1 and no change, or sorry, gradient becomes 0 actually, gradient slope hoti hai. So let me, so basically जो S function है आपका, gradient is slope. So slope इधर भी 0 है, ऊपर भी 0 है, बीच में कहीं आपकी slope different है, ठीक है? So whenever you are reaching the top edge of this curve and the lower edge of the curve, the slope, the gradient will become 0, and of course there will be no change in the weights and parameters. So there are various ways of handling this issue, and one way in handling this in recurrent neural networks is through the use of gates. Of course, that is not the only reason why we use gates there. We use gates for memory also. Okay, but in a standard feed-forward neural network with multiple parameters in all the layers, then this is the main issue. So to avoid this, recent years we have changed the activation function for the hidden layers to be ReLU, rectified linear unit. So this is a very simple function, which is basically so real U of some input parameter AX is basically max of 0 and X. ठीक है? So in other words, कोई भी आपके पास input 10 है value आपकी, output 10 ही होगी. But let's say input आपकी -10 है, वो output 0 कर देगा. So in other words, it is horizontal until your input is negative, and then it becomes linear. तो इसका जो function का जो curve है, so basically इसका जो function curve है वो linear है, horizontal actually, and then linear. So there is no actually saturation on the upper side. Lower side पे it is clipped to 0. And again, this is non-linear because, of course, there is a change in the function from the start to the end. And at one point, of course, there is some discontinuity as well, or a kink, but that typically doesn't make much of a difference because it's just one point. Okay. So researchers have proposed to use this function instead of tangent, hyperbolic, or sigmoid in the hidden layers. And they have shown that this is better at handling the vanishing gradient problem. Obviously, you notice that the gradient would remain 1 always after the value become positive. And of course, it's 0 and the gradient would be 0 at that stage. So this has been proposed, and sometimes they also suggest that this model is computationally more efficient, although that is not always, you can say, reproducible. Why is it efficient? Because the function is simpler. Sigmoid, of course, is a curvature function. You have to find the gradient at each point and so on. This is, of course, a straight 2 linear lines connected at one point. Okay? So this is the motivation, primary motivation behind the ReLU rectified linear unit used as activation function for the hidden layers for deep neural networks. Now let's look at the next problem. The next problem is the exploding. So that was the vanishing gradient problem, now the exploding values problem. So this is again related to that. So sometimes the values, W's that we want to use, W old plus, they will become very large, either on the positive side or on the negative side. And one of the reasons for them become very large is that the gradient does not become 0 or small for a long period of time. Okay? So that is possible, and exploding gradient or exploding values problem becomes more prominent if you use the rectified linear unit, because उसमें आपने देखा वो gradient constant रहता है. So rectified linear unit may reduce the vanishing gradient problem, but it may exacerbate the exploding values problem. But उसका एक simple solution है. The simple solution is we simply clip the values when they become greater than some threshold. Okay? So we simply clip the values. We do not cause it to grow beyond that. So this is commonly implemented in many APIs as well. And this is a trick that people use to handle the exploding values problem. Of course, you can have other things as well. You can modify the activation function also, maybe reduce the gradient at higher level. But the most common and easiest, of course, is to just simply clip the values. Okay, so that's the second thing that I wanted to discuss. The third thing is hyperparameters. So far we have found tons of parameters also. Parameters kya the? What were the parameters? All the W's and B. And of course, when you have a deep network, there will be many different W's and many different B's. And even for GRU, as you saw, we have W C, we have WU, we have WR, we have WO, for example. And similarly, you have B's associated with them. So these were parameters. And these parameters are learned through the optimization process, through the gradient descent approach, applying the backpropagation algorithm. But there are also some hyperparameters. Parameters for the parameters as such, you can say. So what are those? I mean, just I will mention some of those. So there are also network parameters also. So So for example, number of layers. So this is a parameter. How do you decide how many layers to decide in a particular application? I talked about deep neural networks. So कितने layers आपने लेनी है? Similarly, number of units per layer. This is another parameter that you need to decide. Then there's also the issue of activation function. So which activation function should you use? Tangent hyperbolic, sigmoid, rectified linear unit, right? And then there are other architectural issues. Should you use RNN? Should you use GRU? Should you use LSTM? Should you use fully connected or partially connected layers? Should you use CNN? We did not discuss CNN, convolutional neural networks, but you can also use them, and so on. So there are so many things that you might want to decide. So these things are called hyperparameters. Okay? But these are not all. There are many other hyperparameters. So these, I call them.
सर वो स्क्रीन पे नजर नहीं आ रहा आप जो टाइप कर रहे हैं रीलू के बाद से मुझे कुछ नजर नहीं आ रहा
किसके बाद से
रीलू जो हमने किया ना उसके बाद से एक्सप्लोडिंग और ये सब टाइप हुआ नजर नहीं आ रहा स्क्रीन पे
अच्छा
जी अब कर्सर आ गया
बड़ी वो तो मैंने काफी कुछ पहले लिखा था तो आपने पहले बताना है
मुझे लगा सिर्फ मेरे साथ इशू आ रहा है
अच्छा तो what should I do? Should I repeat that? Okay, so we are talking about rectified linear unit. This was the vanishing gradient problem, right? So we talked about then the exploding values problem. Okay. So exploding values problem is exacerbated by using the ReLU, but we can use clip the values. So this is a very simple way of handling the exploding values problem. Okay. So then we wanted to talk about hyperparameters. Okay. So hyperparameters are those parameters that are not W's and B, which are usually learned as part of the optimization process. So I said they were network parameters. So there could be many, so number of layers, for example, number of units per layer, and so on. So you can also talk about activation function to use. You can think about connectivity and so on. Okay? So these are also decisions that you need to make. These are generally put into hyperparameters. And then there are also some optimization hyperparameters. So for example, if you remember, there was a eta in the standard stochastic gradient descent. This is a parameter. But usually there are many other ways of optimizing as well. So you can use stochastic gradient descent with momentum. So there is also a approach. So momentum का भी एक parameter आ जाता है. So this is of course parameters for the optimization technique. ठीक है? So momentum का parameter, and of course oftentimes these are changed adaptively. तो इसमें आप जब literature में देखें, you will see terms like Adams. ठीक है? So this is adaptive momentum optimization, adaptive technique with momentum. And there are also other such names. So these are called in general optimizers. So there are various optimizers available. Which to use is also a hyperparameter. And of course, within each of those optimizers, they will have some values like eta or momentum. Momentum usually is alpha. So वो भी decide करना है. So those are hyperparameters. ठीक है? So these hyperparameters need to be tuned as well. ठीक है? And usually these are tuned using a validation data set. So in the standard process, we have a training data पे आपने train किया, validation पे आपने test किया, but test to fix the hyperparameters. Once those hyperparameters are fixed, then you train on both the training and validation using those fixed hyperparameters, and then finally test on the test set. Okay. So you can think of a large training set, उसको आपने दो में divide कर दिया, एक validation set रख लिया, एक training set रख लिया. Validation would be about 10 to 20% of that training set. पहले आपने train किया with some set of hyperparameters and then test on the validation set. Then change the hyperparameters, then test on the validation set. Change the hyperparameter, test on the validation set. Based on this, you decide which is the best combination of hyperparameters. Once those hyperparameters are fixed, you train on the entire training data set. And that would be your final model, which you then use in future or on the test set. So in general, there are a lot of hyperparameters, network parameters as well as optimization parameters, and there might be other parameters as well. वो मैंने भी आगे मैं discuss करूँगा थोड़ा सा. So for example, मैं वो लिख देता हूँ इधर. So optimization parameters, and then we have what is known as regularization parameters. So इसके भी अपने parameters होंगे. We will talk about some shortly. So regularization के parameters भी होंगे. For example, lambda एक use होता है, ठीक है? And there might be others as well. So we actually running out of time. So the next thing was that we wanted to discuss was overfitting and techniques for handling overfitting. So we had briefly talked about this before as well when we talked about logistic regression, but now some of those techniques would be more specific to neural networks. अच्छा, टाइम 5-6 मिनट रह गए. आज क्विज नहीं है. We will have our last quiz next Monday, inshallah. So, okay, I'll stop here then. If you have any questions for whatever we have covered today, we can do that. And then we'll start from overfitting. And then in the next lecture, we'll also talk about transformers. Okay. So transformer, GRU, LSTM, RNN are available as chapter 9 of your textbook. They are also available as part of the videos. Actually, transformer is not available as part of the videos, but the rest are in the videos. And this discussion on vanishing gradient, exploding gradient, and what we are going to talk about in overfitting, this is not in the book. And I don't have any book for this so far. I'm just taking it from the internet as well as any deep learning book that you might have. And I'm summarizing it for you. ठीक है? So any questions?
सर नॉर्मल जनरल क्वेश्चन है सर. जब हम ये पूरा मॉडल ट्रेन कर लेते हैं और फिर हम इसको प्रोडक्शन पे ले जाते हैं या लाइव कर देते हैं,
जी जी.
फिर सपोज रियल वर्ल्ड से हमारे पास मजीद डाटा आया जा रहा है और कुछ ऐसा है जिसके साथ लेबल्स भी है और कुछ ऐसा है जो अनलेबल्ड है जिसकी हमें प्रेडिक्शन करनी है, किसी के साथ लेबल है, तो हम ऑनलाइन उस वक्त हम उसी मॉडल में ट्रेनिंग ऐड करते जाते हैं या हम वापस से पूरा मॉडल रीट्रेन करते हैं अगर हमारे पास कोई न्यू एग्जांपल्स है या न्यू ट्रेनिंग डाटा है? तो पूरा मॉडल ट्रेन होने जाता है या जो 3-4 एग्जांपल्स नहीं आई है वही पार्ट बन जाती है ट्रेनिंग की और मॉडल वहीं जहाँ पे ट्रेन हुआ तो उसके आगे से ट्रेन होता है?
Actually, if you talk about the modern deep learning techniques, mostly वो पूरा retrain करते हैं हम. Although theoretically आप कहें कि stochastic gradient descent आप on the fly चलाते रहें, but that typically doesn't make much of a difference, especially when you're talking about deep neural networks where you have multiple layers, recurrent layers behind, feed-forward layers behind. So usually we will wait until we have sufficient additional data and then do the whole training offline, using, of course, additional computational resources, because of आजकल के training भी computationally intensive है. You need to use GPUs to make it speed them up. So real time आजकल, at least from what I have known from the industry, नहीं हो रहा ज़्यादा इतना. Previous जो simpler models थे वो होते थे, but modern models जो हैं वो offline ही train होते हैं, और जब train हो जाते हैं, जब production और live कर देते हैं.
Okay, thank you.
Anything else? So we will also talk about things like pre-training, and we have already had some idea about pre-training, but we'll discuss this more formally. Maybe next lecture में discuss कर लेंगे. अभी ideas discuss कर रहे हैं before we start the transformers. Pre-training, transfer learning, and so on.